In their Day 1 convective outlook for July 14, 2010, forecasters at the Storm Prediction Center highlighted sections of the upper Midwest, namely southeastern Minnesota, much of Wisconsin, and northeast Iowa, as having a moderate risk of severe weather. Now, surrounding this area of moderate risk was a larger area with a slight risk of severe weather. So what helped SPC forecasters hone in on this general area as being at risk for severe thunderstorms? Well, the synoptic scale weather pattern, or the big picture, was a big help. And in this case, an approaching 500 millibar shortwave trough was a big part of that. If we look at the 12Z analysis of surface-based CAPE and SIN on this date, we can see that the environment at that time was not very conducive to strong updrafts in the region highlighted by SPC as having the moderate risk for severe weather. There was very, very strong SIN. The dark blue shading here means that SIN was at least 100 joules per kilogram in magnitude. And there wasn't very much CAPE there as well, even though there was very high CAPE values off to the southwest over the plains. But if we want to dial in at a single location to get a more specific idea of the environment, we can look at the sounding from 12Z at Minneapolis, and you can see that there is a layer of SIN. It's shaded in yellow here, and it extends from about 925 millibars all the way up above 700 millibars. And the exact magnitude here is minus 329 joules per kilogram. So that's really, really strong inhibition, and it would take Herculean lift to overcome that, and that's just not going to happen. So the environment needs to change in order for severe weather or severe thunderstorms to develop. And throughout the day, the environment did change, and it did become more favorable for thunderstorms. And in part, that's because as the day progressed, it warmed up, and warming the surface is one way we can reduce convective inhibition. But an approaching 500 millibar shortwave trough also provided a lot of help. If we look at the 6-hour NAM forecast for 500 millibar heights and vorticity, we can see a closed low with a strong vortmax located near the Saskatchewan-Manitoba border. But this vortmax here is pretty much too far north to really create divergence in the risk area, which is farther to the southeast here over Minnesota and Wisconsin. But if you note that trailing around the southern periphery of the trough, there's this elongated lobe of vorticity over North Dakota. There's also some weak vortmaxes over Minnesota. Those weaker vortmaxes around the southern edge of the trough could create some divergence over the risk area, and that synoptic scale upward motion over Minnesota and Wisconsin during the afternoon did help prime the atmosphere for severe thunderstorms. Now, to confirm the forecast for upward motion anyway, here's the NAM forecast for 700 millibar heights, relative humidity, and omega. Now, you may remember that omega is a way to measure vertical motion, and the brown contours in this what looks like a jumbled mess over Minnesota, that indicates negative values of omega, and those correspond to upward motion. The values here were as much as about minus 15 microbars per second, and that's about 15 centimeters per second of upward motion. That's not very fast upward motion in the scheme of things, certainly compared to the speedy updrafts of thunderstorms, but these magnitudes of upward motion are fairly indicative of the upward motion that can be caused by divergence ahead of approaching vortmaxes. The cooling that was induced by this upward motion helped prime the atmosphere for severe thunderstorms by reducing SIN and boosting CAPE, and by 19Z, we can see that the environment had changed quite a bit. You can see that over much of southern Minnesota, SIN had been greatly reduced and down to less than 25 joules per kilogram, so SIN was now weak, and CAPE had skyrocketed over the region, and there were several thousand joules per kilogram of CAPE, so there was a much greater potential for strong updrafts. And some of that change came from the fact that there was surface warming during the day. That helped to reduce SIN and boost CAPE as well. But lapse rates in the middle troposphere were changing too, thanks to that cooling aloft from the upward motion and from falling heights ahead of that trough. To get a better feel for the changes in the lapse rates, we can look at the lapse rate tendencies during the afternoon. Now, this covers the 6-hour period leading up to 18Z, and you can see these positive values across southern Minnesota into Wisconsin, showing that lapse rates were increasing by as much as 2 degrees Celsius per kilometer in that 6-hour period. And the net impact of those increasing lapse rates is that lapse rates in the mid-levels had become quite steep over that region. So these are the lapse rates from 700 to 500 millibars at 18Z, and the shaded areas are lapse rates greater than 8 degrees Celsius per kilometer. That's nearing the dry adiabatic lapse rate. So those are steep lapse rates across the high risk, the moderate risk area. And there was also a pretty significant area of steep lapse rates across northwest Minnesota and eastern North Dakota as well, where lapse rates were nearing 8 degrees Celsius per kilometer or even more. Those lapse rates in that region were benefited by the pocket of cold air in the mid-levels near the core of that 500 millibar trough. On the 12-hour 500 millibar height tendency map, we can see the falling heights just ahead of the trough in the 12 hours leading up to 21Z. You can see the height falls marked by the blue dashed contours here and the even greater height falls that are shaded in blue. And those falling heights help to steepen those mid-level lapse rates and make them destabilize that region as the lapse rates in the mid-levels got closer to dry adiabatic lapse rates. So what was the end result of this shortwave trough priming the atmosphere for deep moist convection? Well, here's the 21Z composite of radar reflectivity, and you can see several clusters of thunderstorms in the region. A couple of clusters over Wisconsin had been ongoing for a couple hours by this point, but new convection was developing back over northern Minnesota as well, where those steep lapse rates were underneath that mid-level pocket of cold air. But furthermore, this 500 millibar trough also had a pretty nice mid-level jet with it. And you can see the fast winds on the southern flank of the trough on this 18Z 500 millibar analysis. And winds at the core of that jet were near 70 knots or above 70 knots. So that's a strong mid-level jet. And the presence of that mid-level jet helps to increase the magnitude of vertical wind shear in the layer between the surface and 6 kilometers. That favors organized, sustained thunderstorms. And in fact, on the 19Z image of radar reflectivity, you can see some discrete thunderstorms in southeast Minnesota. And those were actually supercell thunderstorms that were rotating, and they lasted quite a while. And they actually congealed into the line of thunderstorms that we saw previously on the 21Z image of reflectivity. So these thunderstorms were sustained. They lasted quite a period of time. Hopefully this example does give you a good idea of how features at 500 millibar can prime the atmosphere for deep moist convection. But the details of exactly where these thunderstorms set up are determined more by surface boundaries, and we'll address that later.